Okay, guys, this is my second video. I'm going to teach 7.1 properties of a normal distribution. So let's start with the uniform distribution. Okay, so let's do it. Imagine that a friend of yours is always late. So if your friend is always late, let the random variable x represent the time from when you are supposed to meet your friends until he or she shows up. Suppose your friend could be on time. So if it's on time, that means x is equal to 0, or up to 30 minutes late. So that means x is equal to 30. So with all intervals of equal time between x equal to 0, that means on time, and x equal 30, that means 30 minutes late, being equally likely. For example, your friend is just as likely to be 3 to 4 minutes late as he or she is to be 25 to 26 minutes late. The random variable x can be any value in the interval from 0 to 30. That is x between 0 and 30 inclusive. Again, 0 is on time and 30 minutes late. Because any two intervals of equal lengths between 0 and 30 inclusive are equally likely, the random variable x is set to follow a uniform probability distribution. So let's go here. So now, okay, guys, the definition: a probability density function. A probability density function, PDF, is an equation used to compute probabilities of continuous. Remember, guys, 6.1 and 6.2, we go over the discrete random variable. Now in 7.1, we now work on continuous random variable. So let me read it again. A probability density function, PDF, is an equation used to compute probabilities of continuous random variable. It must satisfy the following two properties. Okay, guys, these are really important. One, the total area under the graph of the equation over all possible values of the random variable must equal to 1. So again, guys, the total area under the graph of the equation over all possible values of the random variable must be equal 1. So the area must be equal 1. The height of the graph of the equation must be greater than or equal to 0 for all possible values of a random variable. So the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. Okay, guys, now you said, oh, Mr. G, still I don't get it. So let me make an example, because when I make an example, it makes more sense. Okay, guys, here we go. So you see that here, again, guys, from 0 to 30, the random variable is the time. So this is the time. The 0 is on time. So your friend is not late, all the way to 30 minutes. So 30 minutes, that means he or she is 30 minutes late. And then the height of the rectangle is 1 over 30. So it's greater than 0, is 1 over 30. So again, guys, this is a rectangle. The area of a rectangle, let me see if I can write it here. So area of a rectangle is equal to a base times height. So again, guys, my base here is 30, because again, it's 0 to 30. So my base, my length or my base is 30 times my height is 1 over 30. And again, guys, if I multiply these together, so 30 times 1 is 30, 1 times 30 is 30, 30 divided by 30 is equal to 1. So that's why the area of this rectangle is equal to 1. So let me erase this. Okay, so now so the area under the graph of a density function over an interval represent the probability of observing a value of a random variable in the interval. Okay, guys, let's make an example. Let's make an example, and then we see what happened here. Okay, so refer to the situation in example 1 that they are friends. He or she is going to be 30 minutes late. Okay, guys, what is the probability your friend will be between 10 and 20 minutes late? So again, guys, I'm going to make a rectangle. Let's see, it's so okay, guys, I don't know why this doesn't work. Okay, never mind. So what is the probability your friend will be between 10 and 20 minutes late? So again, guys, let me show you this. Okay, guys, if this is a rectangle, so you see that your friend could be on time 0 and 30 minutes late. And then again, the length, the base is 30, the height is 1 over 30. And then the question is what is the probability that your friend will be between 10 and 20 minutes late? So this is 10, this is 20. And again, I'm going to make a rectangle. So, okay, guys, what is the length between 10 and 20? So 20 minus 10. So 20 minus 10 is 10. So the length here is the length here is 10. And then the height is 1 over 30, okay? So if I look at that, so let's see if I can make this text. Okay, here we go. So on that. So here we go. Again, this is, yeah, again, guys, I'm sorry that I'm new to this. So I don't know, sometimes it works, sometimes it doesn't. So so again, guys, this rectangle, the base, again, the distance between 20 and 10, this is a 10, the base is 10, and the height is 1 over 30. And again, if I want to find the area, so it's going to be area, okay, here we go. Area is going to be 10 times 1 over 30. So again, guys, 10 over 1 times 1 over 30 is going to be 10 over 30. So cancel 0. So the area is 1/3. So again, let me erase this. So if you guys can see that we find the shaded area in the figure 2a, the width of a shaded rectangle is 10 and its height is 1 over 30. The area between 10 and 20 is 10 times 1 over 30, that is 1/3 as I showed to you guys. So your probability your friend is between 10 and 20 minutes late is 1/3. So now let's go to the second part. It is 10 a.m. There is 20% probability your friend will arrive within the next empty space minutes. Again, guys, in this question, actually, we do it vice versa. The probability is given. Now I want to find the number of minutes that the friend is late. Okay, so let's do it. Okay, so okay, here we go. So again, guys, I'm going to draw a rectangle. So here's from 0 to 30. So 0 minutes to 30 minutes late. And the height of a rectangle is 1/30, correct? Because again, the area of this rectangle is going to be 1 because base is 30, height is 1/30. 30 times 1 over 30 is 1. Okay, now it is 10 a.m. There is a 20% probability. So again, I'm going to say, okay, the 20% somewhere here, okay? So somewhere here, so here is the area of this part of this rectangle is 20%. And again, if I convert it to the decimal, if I convert this to the decimal, is, let's see. Okay, so here we go. Okay, so this is 0.2, okay? So the area is 0.2. So now I know the height is 1/30. So now again, guys, the area is equal to base times height. So the area I know is 0.2. So it's going to be 0.2 equal, we don't know the base. We don't know the base. And then the height is 1 over 30. Uh-oh. So now if I want to isolate the b, I'm going to multiply both sides by 30. So if I multiply both sides by 30, so it's going to be b equal to, so because 30 times 1 over 30 is cancel each other, so b is alone, and 30 times 0.2 is going to be 6 minutes. So it is 10 a.m. There is a 20% probability your friend will arrive within the next 6 minutes. So let me again erase this. So I'm going to show you the actual problem so you guys can see it. So again, guys, you see that this is a rectangle, the 20%, this rectangle is a 20%, the area is 20%, 0.2. So I'm going to write the area is equal to base times height for area of a rectangle. So the base is unknown, so I don't know, I just write base. And height is 1/30 equal, the area is 0.2. And again, I multiply both sides by 30. So 30 times 0.2 is 6. So your friend will arrive within the next 6 minutes. Okay, so now let's go to the next page. Okay, so see. Okay, so now let's start here. A continuous random variable. Again, guys, remember chapter 6, we talk about the discrete random variable. Now chapter 7, 7.1, we talk about the continuous random variable. A continuous random variable is normally distributed. So when we talk about the continuous random variable, it is normally distributed or has a normal probability distribution if its relative frequency histogram has the shape of a normal curve. So if its relative frequency histogram has the shape of a normal curve, then a continuous random variable is normally distributed or has a normal probability distribution. And again, if its relative frequency histogram has the shape of a normal curve. So again, guys, here, if it has a normal curve, that means it's a bell shape. So remember, guys, make sure, understand this, that, okay, guys, if I draw a line, and then this is a bell shape, oops, sorry. So if I make a bell shape like this, okay, so make sure, guys, this line to the each end, to the right and to the left, it shouldn't cross this line. You see that this line? So this, it gets closer, but never touch my under this line, okay? So, and then the both sides. So they never ever should touch this, okay? So, and again, the inflection points we have here and here, the inflection points, again, it's where that the graph change behavior. So these are my inflection point in the normal curve. So again, the inflection point to the left is going to be mu minus 1 standard deviation, and inflection point to the right is going to be mu plus 1 standard deviation. So again, mu minus 1 standard deviation and mu plus 1 standard deviation, and those are my inflection points. And the middle line, it's my mean, that is called mu. Okay, so, and again, guys, these lines never ever touch the x-axis. Okay, so let me again erase this. So So now let's go to the next page. Okay, guys, here. So again, guys, the point at x equal to mu minus 1 standard deviation and mu plus 1 standard deviation are the inflection points on the normal curve. And again, guys, those inflection points are the points that the graph change the behavior. And those are called the inflection points. And then now let's look at here, see what happened, okay? So let me, erase this, okay. So you see, guys, these two bell shape, you see that the standard deviation on both red and blue one, the bell shape, the standard deviation is the same, is 1. But the mean of the red one is 0 and the mean of the blue one is 3. So you see that the actually, if my base, the first graph, the first bell shape is mean is 0 and the standard deviation is 1. And then the second one that is blue is mean is 3 and the standard deviation 1. We shift 3 units to the right, correct? So if the standard deviation the same, we have a same bell shape, but again, it's shifted either to the right or shifted to the left, okay? So here again, the mean is 0, and then the next one, the mean is 3, so we shift 3 units to the right. But look at the next one. Look, the next one, the B, the graph B, the mean is the same, the mean is 0, but the standard deviation of a red one is 1, but the standard deviation of the blue one is 2. Uh-oh, look, guys, here what happened. As the standard deviation increase, so as the standard deviation increase, so you see that the red one is 1, but the blue one is 2, so it's increased, the data is more spread out. So that's why it get more bell-shaped here. So, so as the standard deviation increase, the data is more spread out. So you see that the blue one, we get a more bell-shaped. So now let's look at the properties of the normal density curve. The normal curve, so property number one, the normal curve is symmetric, but it's mean mu. So again, guys, it's symmetric. That means the one half is the mirror of the other half. So the normal curve is symmetric about its mean. So again, guys, if this is again, guys, if this is a bell shape and this is a mean mu, this half is the mirror of the other half. So the normal curve is symmetric about its mean. Okay, so number 2, because mean is the same as median, as the same mode, because remember, guys, in chapter 3, I tell you guys, for the symmetric, if we have a bell shape, the mean and median and mode is the same. So because the mean and median and the mode is the same, the normal curve has a single peak and the highest point occurs at x equal to mu. So that's why, again, you see that again we have the highest point, it's happened in the middle, and because the mean, median, and mode is the same, so the normal curve has a single peak and the highest point occurs at x equal to mu. So And then number 3, the normal curve has inflection points at mu minus 1 standard deviation and mu plus 1 standard deviation. So as I explained to you guys before, so the normal curve has inflection points, mu minus 1 standard deviation and mu plus 1 standard deviation. The area under the normal curve is 1. So again, guys, because the probability is between 0 and 1, so the area under the normal curve is equal to 1. The area under the normal curve to the right of the mu equals the area under the curve to the left of the mu, which equals 1/2. And again, guys, because it's a symmetric and the area under the curve is 1, so the half is the half. So again, guys, let me show it to you guys again here. So again, if this is a bell shape, and again, guys, this is mu, and area under the curve is 1. So obviously, the area under the normal curve to the right of the mu, so to the right of the mu here, equals the area and equals the area under the normal curve to the left of the mu. So obviously this area is equal to this area, so this is 1/2 and this is 1/2, and 1/2 plus 1/2 is equal to 1. So and number 6, as I explained to you guys before, as x increases without bound, gets larger and larger, the graph approaches but never reaches the horizontal axis. As x decreases without bound, gets more and more negative, the graph approaches but never reach the horizontal axis. And again, guys, as I explained to you guys before, so this is a horizontal axis. You see that either we go to the x get larger and larger, or get negative, more goes to the negative. The graph approach but never touch the horizontal axis in the both side. So as I explained to you guys before. So here we go. So now let's go to the next page. So again, guys, number 7, the empirical rule. Let's just review a little bit. So again, guys, the empirical rule says approximately 68% of all area under the normal curve is between mu minus 1 standard deviation and mu plus 1 standard deviation. Approximately 95% of the area is between mu minus 2 standard deviation, mu plus 2 standard deviation. And finally, 99.7% of the area is between mu minus 3 standard deviation and mu plus 3 standard deviation. So let's see. Okay. Let's go to the next page. Okay, I'm going to skip that. Okay, guys, example 4. Let's go over this. Okay, interpreting the area under a normal curve. The serum total cholesterol for males 20 to 29 years old is approximately normally distributed. Again, guys, that tells me that it gives me a permission to use the bell shape. So again, the serum total cholesterol for males 20 to 29 years old is approximately normally distributed, with the mean mu is 180 and the standard deviation of a 36.2. Based on the data obtained from the normal National Health and Nutrition Examination Survey. Okay, draw a normal curve with the parameters labeled. So if you guys see that part A, you see that we have a graph. You see that the graph both to the right and left never touch the horizontal axis. The mean is 180 and the standard deviation is 36.2. And again, the inflection points is going to be mu minus 1 standard deviation and mu plus 1 standard deviation. So 180 minus 36.2 is 143.8. And mu plus 1 standard deviation, 180 plus 36.2 is going to be 216.2. So these are my inflection points. These are my inflection points. And this is my mu, okay? So, and again, these inflection points, it's fine from here, the mu minus 1 standard deviation, 180 minus 36.2, and then mu plus 1 standard deviation, 180 plus 36.2. So we get these 143.8 and 216.2. So let me erase this again. Okay, so now let's go to the part B. An individual with total cholesterol greater than 200 is considered to have high cholesterol. Shade the region under the normal curve to the right of x equal 200. So again, guys, if you see that this is 180, 200 goes to the right, and then I'm going to shade the area to the right of 200. So that means this shaded, blue shaded area show me those people who have a high cholesterol. And then part C, suppose that the area under the normal curve to the right of x equal 200 is 0.2903. You will learn how to find the area in section 7.2. Provide two interpretation of this result. So if the area is 0.2903, so the two interpretation for the area of this shaded region are: one, the proportion of 20 to 29 years old males that have high cholesterol is 0.2903. But again, I love the second interpretation. The probability that a randomly selected 20 to 29-year-old male has high cholesterol is 0.2903. Okay, guys, I'm done with 7.1. And again, I'm going to post it on the Canvas. So, and again, guys, tomorrow morning at 7:15, I'm going to probably meet you guys in the Zoom or Proton. So I'm not sure. So let's see what happened. But again, guys, I'm going to create a discussion board so we can talk, and I will take attendance. Thank you so much and have a beautiful day. Bye.